Right, first ionisation energy is the last of our periodic trends that we have to justify. But before we can justify it, we actually need to know what it is. So the other thing that we need to be able to use first ionisation energy for is, sorry, not first ionisation energy, ionisation energy, is to infer how many valence electrons something's got. So we're going to go through the definition of the periodic trend first, and then if we have time, we'll do how we use first, second, third, fourth ionisation energies to work out how many valence electrons we need. If we don't have time, we'll make that as another video. Okay, so first ionisation energy. The best way to remember the definition or what it means is to actually write an equation like this. So I'm showing I've got 1 mole of an atom in its gaseous state, and I'm turning it into its 1+ ion. So I'm removing 1 electron. It's the most easily removed electron, so it will be one from its valence shell. And the enthalpy is going to be positive, so this requires energy. So basically, this is the definition for first ionisation energy. The amount of energy required to remove 1 electron from 1 mole of an atom in its gaseous state. So they're very particular about how you phrase that in NCEA. So my suggestion is to write it as an equation instead, because they'll accept the equation or they'll accept it in words. So I reckon this is easier to remember because you're not going to miss a word out. The key thing to remember is that these have to be gas. That's probably the biggest mistake I see when marking exams and tests, that people forget the little subscript that these have to be in a gaseous state. The reason that we need it to be in a gaseous state is we don't want to use some energy changing its state as well. We just want to see how much energy it takes to remove the electron. So we're not going to worry about the enthalpy of vaporization or anything like that. The general trend that we observe is that, sorry, let me do mine very quick. Periodic table, which isn't going to be perfect, but it'll be close enough, is that as we go across a period, it becomes harder and harder to remove. In other words, I need more energy. So it increases, first ionisation energy increases across a period. Conversely, as I go down a group, it gets smaller, it decreases. So we need to be able to justify this. And the easiest way to justify this is to do with ionic radius. That's probably the first thing you need to look at. But if you're looking at two atoms that maybe have very similar radii, then there's other things coming into play. So the reason this increases across here, and it's a general trend, remember, the reason that it increases is that primarily the radius is getting smaller and the nuclear charge is getting bigger. So the force of attraction between the outermost electrons and the nucleus is getting bigger. So more force is required to overcome that to remove an electron. And that kind of makes sense because we know that the alkali metals lose an electron very, very easily. If you put them in water and they'll lose their electron. So that's not much energy required to do that. Whereas if I put fluorine in water, it reacts violently for a different reason. It attracts electrons. So it's very hard to remove its electrons. As we go down a group, the reason that the energy decreases is because the electrons are so much further away. Even though you've got a larger nuclear charge, you've got so much more shielding from electrons at lower energy levels that, as well as the increase in radius, there is a decrease in effective nuclear charge. Less effective on those outermost electrons. So it's easier to remove one. Right? There are a couple of little exceptions when you look at your book, and they need to be justified in terms of maximum spin, so where an orbital is half filled, or to do with completed orbitals. So those are other things that you have to look at in this. I'll just put that as a wee list. We've got atomic radius, and that's one of the best ones to use for this. But if that doesn't really explain it well enough, then we need to look, atomic radius along with nuclear charge. But if those two ideas don't explain it well enough, then you need to look at things like completed orbitals, half completed orbitals, so maximum spin, that sort of thing. And of course, complete energy levels are going to be even more stable again. to remove electrons. Okay, so there's quite a lot to consider with these. So they give a lot of scope for an excellence question where you have to look at the difference between the ionisation energies of different atoms. So I'm going to have time to sort of go through the difference, the first, the second, and the third. So this is the first ionisation energy. The second ionisation energy is how much energy does it take to remove the next one. So it's to go from X plus to X2 plus. If I took something like sodium, put that over here actually. So I want to use the Bohr model electron configuration. So I'm just going to show the energy levels because it makes it a little bit easier to understand. 2, 8, 1. Its first ionisation energy is going to be quite low because it's only got one electron in that third energy level, so it's not going to take much energy to remove. As I said before, we know that. Put it in water and it explodes because it loses it so easily. So, there's more happening, of course, but that's a good observation. You can use as anecdotal evidence there. So, its first ionisation energy is very low, or quite low. But its second one is quite high. There's a sudden increase in its second ionisation energy. So why is that? Well, in the first one, it's going from this to this, which has got a smaller radius, a much smaller radius than the sodium atom. Then, in the second stage, we're having to go to Na2+, which we all know now doesn't exist in nature. We have to make it exist. So that's 2 to 7. Well, actually, that's going to take a lot of energy because smaller atomic radius, but it's also got a complete energy level of Na+. So you're actually, it's going to be very resistant, as it were, to having that removed. So, a piece of evidence to help us work out the electron configuration for sodium is to watch what the graph does for its ionisation energies. And if we have the amount of energy on our y-axis and the ionisation energy at the bottom, you see that the first ionisation energy would be quite low, then there's a sudden jump, and then it would slowly go down a little at a time. Okay, so, sorry, not correct. It'll suddenly jump up and then slowly go up like this until you get to 6 of them being removed, and then you're going to have another jump because you're out of the p orbital, and that's how we can use this. So you get these huge jumps of sometimes thousands of kilojoules per mole, and that shows you that you've gone to a new energy level, and if it's just, say, 1,000 or so, then you're probably into a new orbital. So we use these ideas of energy levels to help us work out what the electron configuration is. So we use a whole lot of evidence. That's how we're pretty sure, even though we haven't seen electron energy levels, we've got a lot of evidence. Ionisation energy, emission and absorption spectra, things like that. So that's how we use these. Right, we'll stop there.